First of all, I would like to propose and to ask about the exam date. Do you hear me?
Yes, we hear you.
Okay, so I think that the first presentation should be, let's say, Thursday, December the 2nd, which is okay, uh, at 8 a.m. Okay, so when you have the course, actually, it will be in the same time slot as the Thursday course. You will have the exam. Is it okay?
Well, for me, it is.
Okay, so this is for the first. For the second presentation, uh, I proposed December 9, 1 week later. Okay, uh, again from 8 a.m. So please, okay, please note these two dates and the time. And what I would like by Monday to confirm these two dates for the exam. Okay. Okay. So for this course, we will continue with the coding of a processor core, and we will go into the beta processor and how uh, uh, the code the RTL code for it's developed. Okay, so I will start with a short recap for this processing core. Then I will go through these memory interfaces, a register file, the pipeline register, and in the end, the actual processor the design. Okay. So as I told you, the beta processor, of course, is a 32-bit RISC processor with the 32 registers, meaning that each the number of bits for register encoding is 5. Out of the 32 register, you have 5 dedicated registers. For the implementation, we consider a Harvard architecture, which actually has different memory interfaces for the instruction and for data. Also, we consider a two-stage pipeline. In the first stage, we have the instruction fetch and decode. In the second stage, we have the execute and the data memory access, and of course, the write back into the register file. Now, for this simple example, we'll consider no interrupts and no exception handling. And of course, we won't go into the software part associated to a processing core. So we're not going to go into the tool chain. So for the memory interfaces, as I told you, we will consider two memory interfaces. One memory interface, especially for data, consists of these 6 lines. So you have an write enable, write data, and write address, and you have an read address, read data, and the read enable. Of course, the write part, it's not considered for, or it's not required for instructions, okay, because you only read, or most of the time you only read the instructions. So this is the and basically for instruction and for data, you will have a group of this stuff. Several remarks. As I wrote here, in bus-based system, actually these two memory interfaces will become two master bus interfaces. Okay, you will see what it's master bus. Bus master, sorry. If the two masters, okay, or the two interfaces are connected to the same bus, then actually the Harvard architecture it's for Neumann architecture, because in the end you will reach out to the bus, to the same bus, and you'll go with the arbitration and so on at perform at the bus level. Okay, and there is only one memory address space corresponding to this bus, and so on. Okay, usually this true Harvard architecture is employed when cache memory are used, which in most cases, especially the low-level caches such as level 1 cache, is split in data and instruction. So the register file, actually the register file, it's low size memory, okay, implemented with registers, meaning that it's implemented with D flip-flops. Okay, you'll see that memory kind of memory types of maybe implement with SRAM, especially if you want a fast kind of memory. Okay, and the SRAM usually it's lower cost. Okay, but for small sizes such as this one, you will use usually register files are used. Okay, SRAMs are more efficient when you're considering an k-bit range of memory. So basically, you have, let's say, more than 1 kilobit of memory. Okay, then the most important feature for this register file is the number of ports, because when you have an increased number of ports, you will have higher parallelism. Okay, and this is useful in a very large instruction words kind of architectures. Okay, when you have a low number of ports, when you have a high number, the main disadvantage is that the cost of the register file, it's very high with each additional added port. Okay, the number of ports, it's given mainly by the types of instructions, and in this case we have, for example, for this beta processor, we have the ALU type 1 instruction when we have two source registers and one destination register. Having two source registers means that we need to read, to have two read accesses at the same time, okay, from the register file, and this means that the register file will have two read ports. Also, it will have one write port, because you will have to write back. You have one destination register, and you will need to write back into the memory, into the register file. So the RTL code for a register file, usually what you have the read port. So each port is defined by its address and data. Okay, so you have on the port A, you have the port B. The address, as you can see, it's on 5 bits. Okay, you have 32 registers, so the address is on 5-bit, and you have a write port with the write enable. Actually, the behavior of the read ports, it's you read the data from the read address. For write, when it's write enable, you write the data at the right address. So the main part, the declaration of the registers are in these two lines. Okay, so you have 32 registers of 32 bits. Each register is defined by the signals file reg and file next. Okay, and the register file. Well, I have used here some form of for. Usually, this kind of for statements during pre-synthesis stage, or let's say pre-compilation stage, they are unrolled. Okay, so this is the sequential part. Okay, and here it's the combinational part. The read operation in these two lines, and the write operation. You see that you have these two read operations here perform at reg A read address and at reg B read address. Okay, and of course the special registers with always 0 value, which is this one. Okay, so this will be always 0. Yeah. If you have questions about the register file. Okay, if you don't, then we'll follow for the pipeline. As I told you, we have a two-stage pipeline. The first stage is the instruction fetch and decode. So basically for the instruction fetch, we initiate and we receive the instruction memory read, and we store the instruction into an instruction register, and also during this decode we are performing the extraction of the data from the source registers, okay, which are embedded into the instruction. Okay, also we perform the extraction of the constant which are which is given in the instruction. Okay, the second stage is the executed loads and store. Here we perform the ALU instruction. We perform the read and write address, read the write data address. Okay, and also we initiated the data memory transaction either for a load. In this case, we initiate a read transaction, either for a store where we initiate the write transaction. For branches, we update the program counter, and of course, we write into the destination register the data from the previous instruction. Regarding the pipeline stages, so between these two stage pipeline, we need to have the pipeline registers. One register is for the instruction opcode, okay, because the instruction opcode will determine what kind of operation will be performed in the execute pipeline execute stage. Okay, also the value for the source registers, which have been read from the register file. Okay, the constant in instructions that requires operation with constants, The program counter, we need a program counter for ALU operation in the case of branch instruction, and of course the address for the destination registers. And this is actually the interface for a processing core. When we have no interrupt, basically the interface for the processing core will consist of the memory interfaces, because this is how the processor communicates with the outside world via the memory interfaces. Also, when you have interrupts, you will have in this interface the interrupts. Okay, so you have the instruction memory interface, which is a read, only read. You have a data memory interface, which is both write and read. Okay, because you can the data you can have both write and read. And actually, this is the interface for a processing core. Okay, plus the additional interrupt thing. Okay, good. So usually in the case of processor design, you have this encoding for the instruction, which in this case are the 6 bits used for instruction encoding. Okay, because as you will see, and I told you last week, a very important part, you can view the processing core as a finished state machine based on the instruction register, and actually based where the case for the finished state machines are given by these values of the opcode for these instructions. So the register declarations, okay, we have the program counter, which stores the current address of the address of the current instruction. Then we have the pipeline registers, so the opcode, the source registers, the constant registers, the program counter, the destination register, and the value for the destination for store instructions. Okay. Okay, we have different signals such as for instruction, such as signal for arithmetic operation, and so on. Okay. Very important are the signals for register files. We have a 2-read port register file. So we have these 2 sets of signals. We have one write port. So we have this set of signal. And here we have the instantiation of the register file. First, the 2 read ports, and then the write port. Okay, if you have questions.
Why is the constant register on 16 bits?
Because okay, you may put it on 32 bits, but it okay, it will take memory. Just 1 second. I will show you. Okay, so the constant register one second. Okay. Okay, so just 1 minute. Okay, so do you see here the two types of ALU instructions?
Yes.
Okay, so for the second type, when it's a register plus, well, a register and operation with the constant, okay? The constant you embed in the instruction, okay? Did you understand till now?
Okay.
So actually, the constant, okay, the instruction is on 32 bits. So you can embed, let's say, in this case, a maximum of 16 bits constant, okay? Because the instruction word has 32 bits, and of course you need the 6 bits for the opcode, and in this case you have 5 bits for the destination registers and 5 bits for the source registers, and the rest are for the constant.
Wait, but does that mean that when we have an operation that uses two source registers instead of a source register and a constant, then we only use 6 plus 5 plus 5 plus 5 bits?
Exactly, and as you have seen in the first part, the last, I don't know, with X, these bits with X actually are unused.
Okay, so that's more like a design choice, right?
Exactly.
Okay.
Then this is due to this. First of all, this is the fields. Okay, so the opcode is given mainly by the number of instructions. Okay, how you want to organize instructions. Okay, the register encoding. It's given by how many registers you have. Okay, because for example, if you have 64-bit registers, 64 registers, you will need 6 bits. Okay. If you have 16 bits, 16 registers, you will need 4 bits for encoding. Okay. And of course, the types of operation between registers. And okay, it's a natural way to have, let's say, operation between two registers. Okay, so that's a natural thing. Okay, so other form which is quite found and reduces to one read port, it's to have, for example, the destination equals destination, let's say, plus the source. Okay. You may have also this kind of encoding. Okay, so basically these are, let's say, design choices. Okay, and of course you want to go in order to have a more convenient way of storing instruction in the memory and so on. You want to have a fixed size instruction word. Okay. So for example, in this case, ALU instruction type 1, okay, you have this 21 bits. You won't have 21 bits instructions. Okay, you still have 32 bits instructions, although the last, let's say, 11 bits are not used. Okay, and of course, here for the constant, you again fill up the constant with the bits that remain. Okay, this is somehow, especially when you have branches, this poses a limitation because you cannot branch to the entire memory address space. You know what I'm saying? Because you are limited by this 16 bits. Okay, and you have a 32-bit processor and the entire memory address space is on 32 bits. Okay, so you cannot branch in the entire memory address space. Okay.
Okay, but let's say if we really wanted to have operations with constants or instructions that use constants and the constants to be on 32 bits in this case, couldn't we, I don't know, say that if a certain instruction uses constants, the next instruction slot is actually the constant, and then
Well,
don't know
you can have, but I think you should, you would, okay, it's your choice, but you need, first of all, to put some things on the, to modify the logic in the program counter, okay, because that will need to go from, okay, to pass, okay, through another word. You know what I'm saying?
Yes, yes.
Okay, and also that will mean uh, some modification, which I don't know how trivial they are in the, especially in the linker. Okay, because in the link editing, you actually put the instruction into the memory addresses. Okay, so yeah, so you can do everything, depends on what is the cost for the final product and which is the time development for it. Okay, which basically the development time, it's actually another form of cost. Okay, because working more hours, okay, or more months, okay, actually means more money you have to spend for the development, you know. So yeah, you can do almost everything. As I told you, I've seen very large instruction words uh, with 8 uh, well, 16 read ports, okay, and the cost was huge. Okay, so yeah, you can go with the saying, what you cannot do with money, you can do it with more money. Okay, so but is it something that you want to pay for it? Okay, in the end, did you understood?
Yes, thank you.
Okay, so yeah, that's why it's 16. In this case, it's a 16-bit pipeline stage. Okay, pipeline register. Okay, because you have, in this case, for this example, you have a 16-bit constant. Okay, good. But as I told you, you can do it, but with some modification. Okay, so we have this register file. Okay, and then the first stage pipeline. The first stage pipeline basically contains one important register, which is the program counter. Okay, the instruction fetch logic, it's very simple in the sense that you put the read enable on one. uh, in this case, we do not have stalls. Okay, we didn't implement the stall instruction. Okay, and basically in this case, you read from the instruction memory, you try to fetch all the time addresses, which is normal to fetch addresses all the time. Okay, the read address for the instruction is the program counter, and of course you wait for the instruction, it's the read data. Okay, when you have this kind of the signaling with the if it's available and so on, because you may have memory with some delays, you may have delays on the bus. Here you need to put a condition. Okay, if data is valid, then you perform this kind of thing. Instruction is the data. Okay, so this is the instruction decode. So basically, the read address, it's the field, the source register 1. Source register 2, it's depending on the type of the instruction. So basically, this is yeah, for the source register 2. And this is the constant extraction, which is the lower part of the instruction. Okay. The pipeline registers, as I told you, you have this opcode, which actually the opcode it's opcode next is the most important part of the instruction in. Okay, here is the source, the constant. Okay, here should have also for the source B should have actually with the ALU type 1 here, the type 1, yeah. The program counter, and of course the destination register. Actually, the encoding for the destination register, and here is this slide is the pipeline register update. The pipeline stage 2, basically it's a big case based on the opcode reg. Okay, and you will have very big kind of case. Okay, for each instruction you will have a branch in this case, and you are going to perform the operation according to the each instruction type. Okay, and this is for the jump, this is for the load, and for the store. And the last but not least is the write back. Okay, so this is the activation of the appropriate signals for the write port of the register file. Okay, and yet again there are specific instruction. In this case you have DLU and branch. Okay, you have the load. For store, okay, you don't have any kind of thing, because in the store you need to apply to the memory, so you have to perform write to the memory. And this is for data memory and write. Okay, you perform read for load, you perform write for store. Okay, where the address in the store it's given by the result, and the destination gives you the right data. So, and actually this is for the coding. As you can see, it's more to implement the instruction, and the biggest part of the greatest part of coding, okay, it's actually in this case for the opcode reg, where for each instruction you will need to perform these kind of things. And also for the write back part, also for each instruction which requires write back, you need to have a branch in the case. More easily it's for a load store when you have just 2 or 3 instructions, and you have 2 or 3 branches in the case. Okay, so this is for an example of the coding for beta processor. As I told you, the processor is working continuously, and no stall cycle logic is implemented. When you have stall cycles, you need to stop the program counter, and you need not to, you don't need to initiate instruction reads. Okay. The memory, as I told you, you have 1 clock cycle delay. Actually, in the same clock cycle, you give the neighbor and the address, and you receive the data, okay, in the same clock cycle. And of course, I have considered with no memory conflicts, okay. Also no data dependency, which is more or less quite okay, given that it's a two-stage pipeline. With many stage pipelines, you will need to consider hazard because of data dependencies, okay. Do you know what kind of hazards are due to the fact to data dependencies, or can you give me an example? The chat.
We might change something in a like
You might yeah, okay, I will give you, let's say, an example here. And I just write what are the operation actually. Okay, so you have this instruction, and the following instruction is something like this. So you have these two instructions, okay? And what you need here, when you compute the register file value, you will need to compute based on the last value of register 1, okay? That's the whole idea. So you need to have the result from the previous instruction, which is register 1 equals to register 2 plus register 3, okay? And then you will compute register 5, okay, based on register 1. So in this case, if you have multiple pipeline stages, actually you need to introduce some stall cycles, or to put other instructions between these two, in order to ensure that you finish the first instruction, okay, in order to have register 1. And this is a clear case of data dependency, okay, between instructions. And you need to think that you may have hazards, in the sense that if you're not stalling, for example, stall, it's the basic thing that you can do, you may use not an updated value for register 1 in the sub instruction, okay. Okay, so this is for this course. Tomorrow we will proceed with the memories and the example of memories and how we code memories and so on, okay? If you have other questions. If you don't, we'll meet tomorrow morning. Thank you.
Have a nice day. Bye.
Thank you. Goodbye.
Goodbye.